Good afternoon. My name is Sam Mead, and I will be demonstrating the traffic light for the ECE 3620 extra credit project. So without further ado, let's get right into the demonstration. In front of you, you'll see the enclosure I built for the project. On the left side, we do have the traffic light, which is just a little 3D printed unit that I made with the green, yellow, and red. And that is on port F. Pins 1, 2, and 3. In the middle, we have the 7-segment display, which is on port B. That's taking up the majority of port B. And we also have the switch, which is on the right side, and will control the pedestrian input, because this will be implemented essentially as a melee machine. And that is also on port F, taking place of the internal switch, using PF0. So we will go ahead and get this going for a demonstration. First, let's take a look at what if the pedestrian does not initiate a walk sequence. So if that happens, then we just cycle through the natural sequence, which would be 30 seconds of green, 10 seconds of yellow, and 10 seconds of red. And these, as I mentioned, are essentially states. So we have a green state, and we have a yellow state and a red state. That order will never change regardless of input or no input. So we are essentially, for all other operations involving the pedestrian, going to just be setting a flag to change what happens in the red state. In the red state without any input, we're not going to have a walk sign. So it's just going to go through the 10 seconds and then loop back to green. To demonstrate what happens when you hit the button during green, we'll actually switch right to yellow, because the safety of the pedestrians will not be compromised even if we switch right to yellow. It'll just truncate the green a little bit so that we have a shorter green sequence, and the yellow is still 10 seconds, giving cars more than enough time to stop. The flag is set, and we go through the 9 to 0 countdown. Now, the other behavior that we'd be interested in is what if the pedestrian prompts for a walk during a yellow light. So during a yellow light, the cars are already going to stop. It is actually safe for the pedestrian to go ahead and prompt that, because the cars are going to be stopped on red either way. So once we get to yellow, we can hit the walk button, but you'll notice it doesn't go right to red. This is a safety feature which would guarantee that the cars still have adequate time to stop. 10 seconds all the time for yellow, because either way, cars are responding to that yellow light. So we have, just like in the previous sequence, we have 10 seconds of countdown for the red. Now, how I actually implemented this in the code, you will see better in the project report. But as a quick aside, I did not use hardware interrupts for this. I definitely could have, and it would be a great implementation of that knowledge. However, I did start this before we even got to that lecture, so I figured out a nifty way to do this, similar to how we did, I believe, lab 11 or 10. I'd have to look back at that to verify. It's essentially still using SysTick, but using the software timer. So we have wait 10 milliseconds subroutine within the SysTick file, which we can multiply by what would, in an actual interrupt, be a reload value. So it's just a constant. Like for the green light, we need to multiply 10 milliseconds by 300 in order to get 30 seconds, and by 100 in the yellow and red in order to get 10 seconds. So with the behavior of this, we are more than able to pull for input without actually using an interrupt, because we're just doing 10 milliseconds pull back, 10 milliseconds pull, and all of that adds up to the full value of that light, but it's still non-blocking because we have constant periods of button checking. So we're able to pull it without creating an actual interrupt sequence. So Perhaps I could have gone for the full interrupt, but I had already optimized this for what I had, and maybe it is something I'll do another version of, but I thought that this was a cool implementation of the software version, and as far as operation, it does just fine. So taking a look at the actual connections, the 7th segment, as stated, is in common anode configuration. So we have, the documentation will be posted in the project report, but that was all given, so those connections are just standard for this unit. And we, as I've said, we have that, the 7th segment on port B, taking up most of the pins on port B, and the LEDs and the switch are both on port F. Kind of taking advantage of the natural implementation of port F, where switches live on ports or pins 0 and 4, and outputs on pins 1, 2, and 3. So that is about it for the ports. And as far as physical connections go, I do have 2 breadboards here, really just a convenience factor. One of them is for expanding the amount of ground nodes I can have. So essentially we have this ground node here that connects to all of the ground connections for the LEDs because they are positive logic. And for the switch, which is also positive. So we have, on the other breadboard, we have our 3.3 volt connections for expansion and the resistor for the switch, the pull-down resistor. So that is about it. And while we're here, I might as well do one more sequence. So we're on a green light, might as well hit this where it should go to yellow. I missed it, but we'll hit the button anyways. And this will go to the countdown sequence one last time. That's starting at 9 and going to 0. I apologize for the resolution. It's obscuring the numbers a bit, but they are correct. And that is about it. Thank you so much for listening to my presentation. I appreciate all of your time and your energy in teaching this class. It was very informative, and it's made me appreciate embedded development a little bit more. Thank you.